Okay, on to question 4. In question 4, we have a particle P moving in a straight line. It starts from rest at a point O on the line, and at time t seconds after leaving O, it has an acceleration given by the equation A equals 6t minus 18. Okay, and they say find the distance P moves before it comes to instantaneous rest. So many things to consider here. Okay, the first thing is we're given an acceleration equation and we're asked to find distance. So if we have acceleration and we need to find distance or displacement, okay, we need to consider which direction we're going. So remember the three vectors in mechanics that we'll have are displacement, velocity, and acceleration. If you want to go from displacement to velocity, you need to differentiate, and the same from velocity to acceleration. So we differentiate to get from the one to the other, okay? And the reverse is true as well. So if we want to go from acceleration to velocity and from velocity to displacement, we need to integrate. Okay? So differentiate on the way down, we're going to integrate on the way up. So we have acceleration, we need to get to displacement, so we can see we need to integrate to get there. Okay, now before we even get to our displacement function, we need to consider the time at which they want us to calculate this distance, okay? So they say find the distance P moves before it comes to instantaneous rest. Now it starts from rest, and they want us to calculate the time at which it comes to, or the distance move when it comes to rest again, okay? So instantaneous rest is when velocity is equal to 0, okay? Now we don't have a velocity function, but we are able to get one, okay? So we can say velocity is equal to the integral of acceleration with respect to time, okay? Now this is an indefinite integral, so we're going to have a constant of integration, but they also give us another bit of information that the particle starts from rest, okay? In other words, at time 0, velocity is 0, and so we will be able to cancel out the constant of integration. Okay, so we're going to integrate the acceleration function, and that's going to give us, right, if we take 6t, we're going to raise the power first, so we'll get 6t squared, and then we're going to divide by the new power, which is 2. And the same for the next one, we have t to the power 0, so we're going to have 18t to the power 1 divided by 1 plus c. Okay, so how do we get rid of Charlie? Well, when we start at time 0, the particle is at rest, so when t is equal to 0, v is equal to 0. Okay, we've just integrated and found the velocity function. And so we can say 0 is equal to 0 minus 0 plus c, and so therefore c is equal to 0. So we can write our velocity is equal to 3t squared minus 18t. Okay, the next thing we need to do is find out the time at which this particle is at rest. So the particle is at rest when the velocity is equal to 0. So let's set the velocity equal to 0. Let's say when v equals 0, 3t squared minus 18t is equal to 0. And so we can see we have a common factor there of t, which we can pull out, and we're left with 3t minus 18 equal to 0. So we have two factors when multiplied together equal to 0, therefore at any one time either one of them must be equal to 0. So therefore t is equal to 0, which we could kind of gather from the fact that it starts from rest, therefore at time 0 it wasn't moving. And we can also say 3t minus 18 must be equal to 0. And so t must be equal to 18 divided by 3, okay, which is 6. So the particle is at rest between at 0 seconds, and it's also at rest again at 6 seconds. So now at least we have the time at which we want to calculate the distance. Right, we want to calculate distance, and in order to calculate distance, we need to take our velocity function and integrate again. So we have velocity, we're going to go back another step and integrate. So if we want to calculate displacement, we can say displacement is the integral of velocity with respect to time. And again, just like the velocity, we can say, well, it started at point O, and we want to consider its distance from O, so at time 0, its displacement will also be 0, right? In other words, starting from what we are considering its starting location. So the velocity function is the one that we calculated before. With respect to time, and let's integrate. Okay. Now we can go one step further and we can say, well, we aren't interested just in the displacement function, but we're interested in the displacement, right, between two boundaries. Right? We want the displacement between 0 and 6, and so we can even set that in our integral. Right, and now we don't even have to consider the constant of integration because this is no longer an indefinite integral. Okay, so we're going to integrate this function. So 3t squared, we're going to raise to the power 3, raise the power by 1, and divide by the new power. Okay, we're going to take minus 18t, and we're going to raise t to the power, well, we can add the power, so power 2, and divide by the new power. And we would like this between 0 and 6 seconds. Okay, so we can just tidy up a little bit. You can see we're going to get t cubed minus 9t squared. Okay, now all we need to do is consider, well, take the difference between the upper and the lower bound. So basically we're saying f of 6, take away f of 0. The nice thing is I can see 0 is going to be nothing. So we're going to get, let's do f of 6 first. We have 6 cubed minus 9 times 6 squared. And we're going to take away 0 minus 0. So 6 cubed minus 9 times 36 is equal to minus 108 meters. Okay, so we end up with this negative displacement. Does it mean we've done something wrong? No. Remember, displacement is just it's a vector, so in other words, negative displacement just means we've gone in the opposite direction. Okay, so we're starting away from where we started. Okay, but distance, what we've been asked to calculate, is a scalar, which means it cannot be negative. So we can just say that distance traveled is equal to 108 meters. Okay. Now, if you're wondering and getting confused, why do we get a negative answer? So let's go and have a look at this graphically. Right. So here's the equations that we started with acceleration. So we know that when acceleration is equal to 0, right? We know that acceleration is the change in velocity. When acceleration is equal to 0, that means our velocity has a turning point, right? In other words, it's going to change direction. Okay, so you can have a look there, roughly where our acceleration is equal to 0, we have a change in velocity. Okay, our velocity has gone from being going in one direction, well, not going in one direction. It's our velocity was getting faster and faster in the opposite direction, and now we are actually slowing down. Okay, we're still going in the opposite direction, but we're slowing down. Okay, so we're on the way back to where we started, hopefully soon. Now we know that displacement is actually calculated from the area underneath the velocity function. Okay, and if you have a look, our area is below the x-axis, which is why we get a negative value. Because remember, the integral gives us signed area, and the area is calculated from the y-coordinate, right? Lots of tiny pieces chopped up, right? And we use our y-coordinate as the height, and since our y-coordinate is below the x-axis, we're going to get a negative area, right? But like I said again, distance isn't interested if you are negative or positive. Distance is always positive. So you need to remember that. If you don't change that to a positive number, you will lose the mark.